Welcome back to the video lecture series for Introduction to Data Programming using Scala. In this video, we're going to continue talking about binary heaps, but now we're going to show how we can actually view them as arrays. And indeed, when we implement our binary heap, we're not going to implement it using an actual tree structure where we have nodes with left pointers and right pointers. The reason is that it turns out that's somewhat challenging to do. And why is it challenging? Well, one of the problems with doing it that way is the question of how do you answer the question of where does the next thing go? And when we look at this picture, it's very easy to see, well, it goes over here. Okay? But if you only have a pointer to the root, how do you know where the next available spot is along the base? In addition, doing the tree, there's a lot of overhead for keeping nodes with left pointers and right pointers. And as you might have seen with the BST, certain operations can be challenging to code. It turns out there's a much better way that we can do this. And so I'm going to go ahead and put some numbers on our nodes here. I'll make them little numbers. I'll make them a different color so they stand out. Okay, so let's copy that. 2 is going to be labeled as number 1. The 4 is number 2. 3 is number 3. The 7 is number 4. So I'm going to number them in a breadth first order, going across every level. 5, 6, and last up, at least for now, 7. Okay. So the question is, what is significant about these numbers? Okay. We're looking for a pattern here. And it turns out that the pattern that we're looking for is the fact that if you take any node and its left child, you'll see that the difference between their numbers is a factor of 2. So 1 to 2, 2 to 4, 3 to 6. If you go with the right child, it's a factor of 2 plus 1, which means that if you pick any node in the entire tree, given this index, you can find the index of its parent by doing integer division by 2, because 5 divided by 2, we throw away the remainder, and we just get 2. 4 divided by 2 is obviously 2. So there's this nice mathematical relationship between this index value here for any given node and for its parents and children. This only works if I start numbering at 1. And so what's going to happen is I'm going to represent my binary heap here not as a tree, but instead simply as an array. And actually, I guess I'll put a pound there. I'm going to leave the first element blank. And then the other elements are 2, 4, 3, 7, 6, 5, 9, in order going through. And so you'll notice the 2 is at index 1 in the array. There's a default value at the first element. We don't really care what it is. So in certain implementations, many people will take out that value and make it so these start at 0. But when you do that, you break the nice mathematical relationship here, so you have to do a whole lot of plus ones and minus ones. For a heap sort, which we're actually not going to look at, you have to do this because otherwise the heap sort doesn't work. But for just a heap, it turns out that in my opinion, the overhead of keeping one extra value, which in Scala is just going to be a reference. I'm only going to use an extra, for example, 4 bytes, maybe 8 bytes on a 64-bit machine, and I'm going to use that much memory for every entire heap, the whole priority queue. Whereas if I take this down to 0, if I take out that, I wind up having +1s and -1s that are involved in every operation. So I actually slow down every operation. I would rather exchange a small amount of memory per heap and make things go faster and make my code easier to work with, so that these mathematical relationships are held, than to kind of be stingy with the memory and then actually slow things down. So given this, we now have enough information that we can actually start to consider coding our binary heap. It's going to use the same interface we had before for our priority queue, but we're going to actually base it upon an array. So previously we have written a priority queue, has an enqueue, a dequeue, an isEmpty, and a peak, and we even wrote a sorted doubly linked list based priority queue. And now we want to create another priority queue. We'll call it the heap priority queue. I'm going to leave out the detail that it's technically a binary heap, and there really is a difference between different types of heaps. For now, the only one that we're considering is that. And just like with my sorted linked list, here I definitely need to have an array. So I'm going to need to have a manifest. I need to pass in a function that is going to compare values, and I'm going to extend my priority queue. So let's go ahead and copy over the methods from my priority queue to make things more happy. And also, I'm going to declare inside of here a private val. We'll call it heap, and it will be a new array of A, and we'll make it of size 10. Okay. And this is unhappy out because I'm not actually returning things. In addition to that, the array, this is not going to be able to stay as a val, is that it's going to have to become a var, because once we add more than 10 things, we're going to have, or actually 9 things, we're going to have to make it bigger. Private var back is an integer, which I'm going to use to keep track of the index of basically the next blank in there. And since we're not using index 0, back will start off as 1. That makes some of these things easy. isEmpty is back is 1. Peak is return heap sub 1. We'll put in a comment there so that this compiles. I will put that in, and we'll put in a to-do there as well. And this is where we're going to stop. So in the next video, we'll come back and we'll work on our enqueue and our dequeue, where we'll actually implement the procedures that we went through graphically in our previous video.